Welcome to IDSP-5. This is our fifth video in the DSP unit of the Digital Audio Signal Processing course. In this note set and the next one, we're going to talk about changing the sampling rate of a digital signal. And we'll go into some of the details, not as deep as we might go. This chapter in Porat's DSP book goes into a lot more detail and a lot more ideas and characterizations, but we're just going to hit the main ideas in this note set and then one particular scenario in the next one. So here's the idea. We've got some signal x of n, and it's a signal that's been sampled at some fs. We'll call that fs old, and we have some magic box that will somehow convert it into samples that are at some new sampling rate. So here's the thing. There is some x of t that is the underlying continuous time signal, and both of these correspond to effectively, ideally, exact perfect samples of that continuous time signal made at some rate. So this one's at that rate and this one's at that rate. That's the idea. And a lot of students go, wait, how can I do that if I've just got samples at some particular rate? But you know that Shannon's theory tells us that these samples can allow us to perfectly reconstruct that. And then we could physically take samples at this new rate. So why couldn't we just bypass going back to the continuous time? If all the information in here is available to create this, that should be sufficient to create that. And there's some trick to doing that, and we'll have to take a look at that. So that's what we're looking at, how to change the sampling rate of some particular discrete time signal. We've been given at a specified sampling rate, and without reconstructing it and resampling it, create a new version of that continuous time signal sampled at some other rate. That's the idea. Now, why would we want to do that? That's a good question. I'm going to address things from an audio point of view. So sometimes we might have data from one medium. So this might be from a CD, and that's sampled at one particular sampling rate. It's actually 44.1 kilohertz. And we might want to convert it into another format, which is DAT, digital audio tape. Not as common a medium anymore, but we might want to do that. Or actually, we might want to go the other way around. So DAT is at 48 kilohertz. So we might want to convert back and forth between those for whatever reason. We've got something recorded on a DAT and we want to put it onto a CD, something like that. Well, let me back up. And there might be physical audio systems that are running at different sampling rates and we want to interconnect them, but we don't want to have to go back to the continuous time world to interconnect them. So we might want to do that. There are certain tricks that we'll see way at the end of the course when we talk about the nature of A to D converters and digital to analog converters, or ADCs and DACs. There are tricks inside those that we can play if we can do sample rate changes. So that's another reason. We won't see that for quite a while, though. Another thing that we'll see as we get into the middle of the course, we'll be talking about implementing nonlinear effects. And we'll see that when you apply a continuous time signal to a nonlinear effect, it actually increases the bandwidth of that signal. We did see that a little bit when we were talking about measuring the impulse response of a system, and we saw that if it had some nonlinear characteristics, a sinusoid at a given frequency would come out with a whole bunch of harmonic components at frequencies higher than the original sinusoid. So those higher components should be sampled at a higher rate, those higher frequency components. So we'll look at implementing nonlinear effects using digital signal processing and being able to first upsample, apply the nonlinearity, and then downsample. So upsample is increasing the sampling rate, and downsampling is decreasing the sampling rate. So that's an idea that we'll talk about. So there are two fundamental operations involved here, and I just alluded to them without the name, the fancy name. One is called decimation, and that is strictly decreasing the sampling rate by some integer factor. So m here is assumed to be an integer. So you take your old fs, divide it by an integer, and you get a new lower sampling rate. And so we'll have to look at how do we do that. Now, just a caution, we know that if we sample too slowly, aliasing will happen, and there will be could be some problems. So we can't necessarily do this willy-nilly, so to speak. We have to make sure that it is viable to do that. And so we'll talk about that as well. The other one is called expansion. And technically, we'll see that the word expansion is not quite what we want completely, but it's half the way there, as we'll see. But that's the idea of increasing fs by an integer factor. So the key here is these two basic operations involve integer factors. And so it makes sense that we can combine both of those. We can go up by a factor of L and down by a factor of M. And so now the rate change would be by a factor of L over M. And so by picking L and M to be various integers, we can essentially get any rational factor that we want. There are some caveats there as far as the implementation of those go. And we'll address that in the next set of notes as well, to some degree. So here's what we're going to do in this set of notes and the next set of notes. First, we're going to just look at how we do these two things by thinking about what happens in the time domain. And we'll see that the decimation step is pretty obvious. The expansion part will leave something incomplete. It'll leave the process incomplete, and we'll say, oh, it's not quite right. We'll need to fix that. But to understand what we need to do to fix it will require us to study what happens in the frequency domain. So by that, I mean, look at Z domain. That's a generalized frequency domain. And also look at the DTFT view, or the Fourier domain. So that's going to require a little bit more mathematical work, but it'll really give us all the insight that we need to understand how this is working. And then once we have that, we can take a look at some issues that arise specifically in audio applications, although arises elsewhere in other applications as well. And in particular, we're really only going to look at one issue, and that's how to implement this rational change through a bunch of individual stages, one after another. And that's something that pops up in audio applications a lot. There's a lot of other things that we're not going to cover. So things like polyphase methods and things like that do show up in audio, but I didn't want to spend a lot of time on those things to keep us from getting to more audio specific things. So here's how we visualize decimation. So I'm showing a t-axis down here, and I'm showing some samples of a signal taken from some signal, x of t. And you can see I've aligned this so you can kind of visualize what the sampling interval is. So the spacing between those is t sub s, and that's equal to 1 over f sub s, whatever that f sub s happens to be. I can't really tell from this diagram. Okay, now we want to reduce the sampling rate. So that means increasing the sampling interval. And we need to, in this case, we're talking about m-fold decimation, where m is an integer, remember. I didn't say that explicitly on this slide, but I did on the previous slide. So here m is an integer. And so what does that really mean? Well, here's an example for m equal to 3. We would take, that means our sampling interval is increased by 3. So instead of taking this as our sampling interval, we really take that as our fundamental sampling interval. So what does that mean? We would keep this one and we would keep this one, but we can just throw those two away and then throw those away and throw those away and so on. And so we end up getting a sampled version of the original signal, but sampled at a lower rate. So here the rate is 1/3 of what it was before. So whatever it was earlier. Now, it is important to notice that I'm using two different variables for the indices here. Both integers, because they're counting samples. But we see that for the case of big M equal to 3, there is the relationship that 1 on n corresponds to 3 on m, and 2 on n corresponds to 6 on m, and so on and so on. And so that leads us to a simple mapping. This thing here, this relationship maps the output index. That's this one down here, the output of our sampling rate changing scheme, to the index that we go back and grab. So when n is equal to 0, m is equal to 0. But when n is equal to 1, m is equal to m, capital M, which is 3 in this case. So this is just a nice little way to keep track of that. And this just means for n running through the integers. So the set capital Z is a standard notation for the integers. And I'd like to call your attention here. We've been calling this Y and calling this X, but there's a nice way to keep track that Y is the m-fold decimation of X. We just use a subscript that looks like that. Sometimes we'll put it in parentheses. Sometimes we won't, but that's what it means. So that's just pure notation. So let's look at the rule for this m-fold decimation. It's very simple. It's just based upon this idea. So here's our new notation for the m-fold decimated signal of X. It's just the original signal with capital M, n plugged in. So now as n goes through 0, 1, 2, 3, and I can do the negative ones as well. But as n goes through the integers, this is just going to jump every m through the original signal. That's all that does. And so there's a little example, just like we saw on the previous slide. So that's all very nice. So a lot of this is pretty simple. This is our time domain math view. It hardly seems to be much math at all. And this is really how we do it. But to understand what that does to us, whether we can do it without aliasing or can't do it without aliasing, we need to look at it in the frequency domain. Now, before we get to that, let's do the expansion in the time domain. And remember, I alluded to the fact that this expansion isn't really complete. We'll see how to complete the process after we figure out how this works in the frequency domain. That will inform us what we need to do to complete this. So here's some signal at some sampling rate, and I'm using, again, little m here as my index. So I'm taking samples of some underlying continuous time signal every capital T sub s seconds, whatever that happens to be. Now, here's the trick. This is why we call this expansion, it isn't the final thing that we want. What we're going to do is tack on L-1 zeros to each input sample. So there's the trick. So here's an input sample, and now I stuff in 2 zeros. And here's a sample, and I stuff in 2 zeros. This is for the case of L equal to 3. Should have said that explicitly, but I didn't. And so on and so on. Okay, so that's the idea. And you can see this clearly does not end up with a faster sampled version of X. It's just got these zeros stuffed in there. So what we're really doing is using those zeros as kind of time markers. We're going to fill those zeros in with the right values later, but first we have to figure out how all this works in the frequency domain. So again, note the two different indices used. And now we have this mapping. So as n goes through the integers, we have this mapping now. Before it was big M times little n, now it's little n divided by L. And this is going to help us understand how to map these and where to stuff in zeros. And we'll see that on the next slide. And again, here's our notation. We use an up arrow. It's not important whether we use L or M or some other symbol for the integers. The fact that it's trying to increase the sampling rate is indicated by an up arrow. And you can see on the previous slide, if we go back, we're using a down arrow to show reducing the sampling rate. Okay, but again, remember that technically we're not there yet. This does not really mean that we get a signal sampled at a higher rate because we've stuffed in zeros. However, the down arrow one does mean exactly that, as we just saw. Okay, so a little oddity there. Let's look at this mapping. So if we let n go through the integers, and L is an integer, some of these things are going to be non-integers. And so M, what input index sample should I go back and get? There isn't any. So that's the key. If n over L is not an integer, that's where we stuff in a 0. If n over L is an integer, then that's where we go back and grab the sample. So this is just a mathematical equation that expresses what we showed very simply here. Keep the samples, stuff in zeros, and then re-index. That's the idea. Okay, but this is the mathematical view of that. And here's what we have for that for L equal to 3. Okay, now to understand all this, we look at the frequency domain. Now, remember, we already said that M-fold decimation really gives us what we would expect, the signal sampled at a lower sampling rate. So that's nice. Let's start off with some notation. First of all, I am adhering to Peratt's idea of using a superscript to indicate that the function we're talking about is a Z transform. As we go through this set of notes, you'll see how helpful that is, because you might say, well, but it's got a Z here, so can't I just use that? Well, no, because we're going to be stuffing things in, subbing things in for that Z here in the argument, and we might lose track of what function is this? So the superscript tells us that. So these three notations will be used interchangeably, although I do tend to use this one. This one just says take the decimated signal and take its Z transform, and you get a function of Z. And this one says imagine the Z transform for the original signal after the effect of decimating. That doesn't mean that you're decimating in the Z domain. That doesn't really mean anything, but that's it. So that's why I like this, because remember we said X of down arrow M of N is our signal. So that notation just follows through. So remember, superscript Z is just there to help us remember that it's a Z transform. So the question we're going to answer is, if I start off with a signal that has that as its Z transform, and then I decimate the signal, what's the Z transform of the decimated signal look like? Oh, and I should point out that the notation is similar for notating the DTFT, although there I use a different superscript there. We'll see that when it happens. And also there's similar notation for the expansion case, where we'd have an up arrow and some symbol representing the integer. Okay, so here's the question that we want to answer. And before we set off to answer it, this is a good habit to get into. Ask yourself, what do I expect it to look like? Well, we know that I'm sampling slower, so we expect that maybe aliasing might be more of a problem. So there's more of a possibility for higher frequency things to show up down in the original spectrum. So that's what we expect. And when we finish, the answer should look just like what we would expect if we went back to the continuous time and sampled it at a lower rate. So keep that in mind. So like I said, the lower FS causes spectral replicas to move down to lower frequencies. All that is things that I just said. Now, to answer this, we're going to use this thing called a comb function. And at first, it's not going to look like it's doing anything, and then suddenly it will jump into play. And that's kind of why we use it this way. So this part here is just defining what that comb function is. So let's look at it down here. It's going to depend on a subscript m, which will be an integer. And so here I'm showing c sub 3m, and you can see what it is that we want. We want a 1, then 2 zeros, then a 1 and 2 zeros, and a 1 and 2 zeros. So out of every 3, we have 1, 1, and followed by 2 zeros. So that's the way to do it. This notation might be the easiest to see that. We've got mod m applying to n, so as here I'm doing m and here I've done n, so I guess I should change that to n. As n goes through 0, 1, 2, 3, and so forth, the mod is just acting like clock arithmetic, except now you just have 3 hours on your clock. So we get 0, 1, 2, and then 3 mod 3 is back to 0. So we get the next thing. Okay, so that's how that works. Just walking your index around around a clock. And when we get back to 0, that makes this delta function pop back up. And then we have non-zero, and then 6 mod 3 is back to 0, so the delta function pops up. So that's one way to do it. Another way to do it is to think about it as a sum of a bunch of different delta functions. So for k equal to 0, this is just this one with zeros everywhere. And with k equal to 1, it's just this one with zeros everywhere else. And then k equal to 2, it's this one with zeros everywhere. And then we just add those all together. And notice that each one has zeros where all the other ones have ones. So they just add together to create this. So that's these two notations. Where does this thing come from? Well, I'm not going to prove it, but it's pretty easy to see. This is a periodic signal. And so there is a discrete time version of the Fourier series, and it looks just like this. And I've just, again, used this W sub m thing that we encountered in our notes on FFTs. So we're just adding together a bunch of exponential terms that look like sinusoids of different frequencies with Fourier series coefficients in front of each one. But it turns out that each frequency has the same Fourier series coefficient, so it gets pulled out in front. So I don't want to dwell on this too much, but this is a classic result that shows up a lot in signal processing, especially when we're using this comb function. So we're going to use this, and remember that W sub n is e to the j 2 pi over m, so this is just a sum of a bunch of different complex sinusoids. So nice. Time domain views of the comb, and a frequency domain view. We're analyzing in the frequency domain, so it makes sense to think about this thing there. Okay, so let's do the decimation and see what its Z transform looks like. If we can find its Z transform, we can then find its DTFT from that. So that's the path we're taking. So here is by definition what the decimated signal is. And so now what I'm going to do is insert this here. And really that doesn't do anything because I'm jumping every M. So let's go back and look at this. If in this case M is equal to 3, if I'm jumping every M, I'm getting this one, jump, this one, jump, this one. It's all ones. So this is all ones. So it doesn't do anything when I multiply it by this. It does nothing. So at this point you might say, then why did I put it in there? Well, just watch. So now I'm going to take the Z transform of this thing. So this is by definition. So here is this thing substituted in here using the form that we had times Z to the minus N. That is the form for taking the Z transform of this decimated signal. Well, now let's take a look at what it looks like. It's always good when you're dealing with these infinite series to just write out a few terms and see what it looks like. As I let n go through the integers, I'm going to get x of 0, z to the 0. Notice that I don't put c sub m down here anywhere, because remember, this doesn't really need to be there. It's equal to 1 for all n. But let's leave it in here, but down here we'll ignore it. So I get x of 0, z to the 0, x of m, because when n goes to 1, this goes to m, but n equal to 1 gives me z to the minus 1, and so forth. So I get a 1 out here and a 1, a 2 and a minus 2, and so on and so on. So we can now visualize what that looks like. So there we have that. And now let's do a change of variables, and now you'll see where this comes into play. So I'm going to do a change of variables on in these three positions. So if I change this to n and I change this to n, this must change to minus n over m. But remember, now as n goes through its integers, this thing is turning on and off some of those terms. So let's see what we get. When n is equal to 0, I get x of 0, cm of 0, so that's a 1, times z to the minus 0, or z to the 0. Now when n is equal to 1, I'm going to get x of n times 0 times z to the minus n over m. There it is. It goes away. And in fact, that won't pop back up again until n hits m. So there's going to be m minus 1 zeros. That's the action of the comb function. And that's why I put it there. And so on and so on. So now we see what that little form down below looks like. And we recognize there's the action of the C sub m n. Okay, so now we can take this form here and we replace this by what we had for C sub m of n. That was what we had on the previous slide here. So this was our Fourier series representation. It's a sum over m, but it's a function of n. So I'm going to plug that right in here. So there it is. And I've left this here, and I've left this here. Beautiful. Okay, now listen, when you're dealing with things like this in DSP and you have two sums that show up inside a result, almost always, maybe not always, but almost always, the next step involves interchanging the order. You know, and mathematicians would say, oh, you got to check some conditions, but DSP engineers and researchers just say, let's just charge forward. So now we're just going to manipulate. I rewrote what we had on the bottom of the previous slide, and now you can see that I've interchanged the order of this. And so now, and I've pulled the 1 over m out in front because it is not a function of m or n. So I've pulled that out. And so now we've got this. And so now here's where that superscript comes into play. Let's just look at this line here. Suppose that I didn't have this there, and I didn't have this there. I just had a z there. What is this thing in the square brackets? That is the z transform of x. So this would be the z transform x superscript of z. That's the thing that is inside this parenthesis. But now if I remove all that blocked out stuff, all that means is wherever I had the z before, right there, I'm going to erase that. I take all of this stuff and it plugs in there. That's why I like that superscript z, because I look at this thing and I go, does that tell me it's a z transform? Well, there is a z in there, but it's a crazy thing. So it's the z transform of x, not the decimated one, the original one, with z replaced by all of that stuff. Interesting. And we get a sum of those things for different values of m, little m. And we get a 1 over m out in front. But look, this is the least important part of this equation. This machinery is the important part. So there it is. We answered our question, although the answer is not terribly illuminating. We'll see that we get more insight by converting this not into Z transform, but converting this to DTFT. Then we can interpret what this means. But basically, this is saying that the Z transform of the decimated signal is the Z transform of the original signal with some machinery going on, and we add a bunch of those machineried things together. Well, what does that machinery do? To see that a little bit better, let's convert to the DTFT form. So remember, to do that, that means that we're evaluating Z on the unit circle. So Z is constrained to complex numbers whose magnitude is 1 and whose angle goes between minus pi and pi. Little bit of a warning, I'm using theta here where I have previously used capital omega as the discrete time frequency. So that's in radians per sample. Why do I do that? Well, Peratt does that in his book, and I'm basing these notes on Peratt's book. Okay. Full disclosure, I borrowed these notes from some earlier course that I taught that was completely based on Peratt's book, and I just didn't feel like going through and changing all the thetas to omegas, capital omegas. Once they're inside an equation editor, it's hard to do a global search and replace. So I got lazy, and I did that. So we're going to replace Z by that. But what we're really interested in is Z to the 1 over M. That's going to get replaced by E to the J theta over M. So let's do that. And remember our definition of W. If we look at W sub capital M raised to the minus little m, that's just this thing. So what is that? Well, that's just a complex number whose angle is 2 pi little m over m, or m over m is a fraction of 2 pi. And so remember, we're going to let little m run from 0 up to capital M minus 1. So if we do all that, we get to the DTFT of the decimated signal. And here you can see I am using a new superscript. That just means that this is the DTFT of the signal. Remember, I used a Z superscript to show the Z transform. Here I'm using a superscript F to capture the F in the Fourier transform. And it's discrete time, so that's why it's the DTFT. So this is, if we apply these things, you can argue that you get this thing. Remember, we're multiplying by this thing raised to the n. That looks like a sinusoid, a complex sinusoid, and that's where we get this frequency shifting from. Okay, so without going through the details, you can try to work them out yourself, or you can just be trusting at this point. This is not a course on the details of multi-rate signal processing. We're just trying to get to a point where we can use these results, so believe it, okay? But let's look at what this does. This capital M down here stretches the spectrum, and this machinery shifts those stretched spectrum. So we're going to have the original spectrum stretched and then a whole bunch of shifted versions, right? Because M goes through a bunch of different values. And then all those spectra get added together. So aside from the stretching part, the shifting and adding together looks an awful lot like the spectral replica terms that show up in just regular sampling theory. Go back and look at my review notes, and I covered that. So that's the idea. So here's how we think about this. We take xf of theta and we axis scale it. That's the stretch to give this. And then we take the theta here and replace it by that. That's the shift. So we shift by 2 pi m to get new replicas. And so no surprise. Decimation adds some additional spectral replicas, but of a axis scaled version of the DTFT. So that makes complete sense. Let's look at some pictures. I'm a firm believer in looking at pictures to understand mathematical results. There is no shame in that. So let's start with an original signal. I'm doing it as a function of theta. So here's the DTFT of the original signal, plotting it on the theta axis. Remember, our minus pi to pi is our main region. Everything else is a periodic replica of that. So we see all of our spectral replicas there. And I'm showing a case where the upper edge is at pi over 3. So if we think through our sampling theorem, that's telling us that this signal was actually sampled 3 times faster than it needed to be. If it was critically sampled, we would see something that fills the minus pi to pi, and this would also come down here. We know that's critically sampled because if it were sampled any slower, we would get this out here and this up here, and there would be aliasing. So it's important to think that way, that the faster you sample a given continuous time signal, you look at its spectrum is going to get squished further and further inside the minus pi to pi range. That just comes from understanding the original idea of sampling. So we see this is oversampled by 3. That means we can decimate by a factor of 3 without creating any aliasing. And let's see. And again, this is all theoretical because this is a perfectly ideally band-limited signal. None of this can really happen exactly like this in the real world, but if we can show that it can happen theoretically and ideally, then we can get as close to that as we want in the real world. Okay, so remember we need to scale this, axis scale this. So we look at theta over 3. So that's a math function or math operation that we know about. It stretches things, right? When theta is equal to pi, we're really going back to pi over 3. So that point corresponds to that point. So it just stretches it out by a factor of 3. And this is our m equal to 0 term in that sum, right? There's no shift on this. But now all the additional terms are that thing shifted. So Let's look at it. Shifted by, oh, I should say one other thing. Let me back up. What else is going on here, right? This thing gets stretched out, but this thing also gets stretched out. Not only made wider, but its center gets moved out to 6 pi. So this whole thing gets stretched out by a factor of m, which is 3 in this case. Okay, so here's our m equal to 0. Now we're going to shift it. Shift it by what? 1 times 2 pi. That's what's in that formula. And so now it gets shifted, and it's going to be a shift to the right. So this moves out to be centered at 2 pi. This moves 2 pi. This moves 2 pi, and so on. And I should really have dots here to say that this stuff goes on and on and on and on and on and on. Okay, so that's that. And there's the m equal to 2. And remember, we only had 3 terms. M equal to, capital M equal to 3. There was m equal to 0, 1, and capital M minus 1. Those are our 3 terms. And so now that's just another 2 pi over, and 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 so on, and so on. And so now, let me show you on the next slide, there is the m equal to 0 term. So I've just started, I'm basically just showing from here down. We'll look at those terms again. There's the m equal to 0, the m equal to 1, and the m equal to 2, and now I've color-coded them and style-coded them. And remember, our formula says the DTFT of the decimated signal is the sum of these 3 things, and there is the sum. And notice that they do not overlap. There's nothing else lying in the minus pi to pi other than the m equal to 0. That's the condition for no additional aliasing occurring. So we were oversampled by a factor of 3. We could decimate by 3. And now we end up getting something that looks like it's critically sampled. And all of these things that come from that formula that we showed with the sum create the additional spectral replicas that now need to fill in the gap after the stretching. Beautiful, 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 beautiful. Okay, so some insights from this. I just said it. There will be no aliasing if the signal that we are decimating has a spectrum that's 0 outside of the pi over m to minus pi over m up to pi over m. And we just have a special name for those signals. They're called mth band signals. You can't really have one in the real world, but we could have an approximately mth band signal, something like that. So that's the idea. And all of this fits in nicely with our original ordinary sampling theory viewpoint. And we saw that an mth band signal that can be decimated by m and leaving no aliasing or creating no aliasing, it's going to be critically sampled. It will fill the minus pi to pi band. So those are things that we could see from this. Another insight that we can see is that we're not really changing any physical frequencies in the signal. If we take this signal and we play it back at this sampling rate, it'll sound exactly the same, since no aliasing occurred. It will sound exactly the same as playing back that at its new sampling rate. So you just run these samples through a DAC running at 60, run these samples through a DAC running at 20 megasamples per second, and it will sound exactly the same. We can see that mathematically, or at least graphically mathematically. Here's our original spectrum. We saw it lies between minus pi over 3 up to pi over 3. And here we're considering the case where the original sampling rate was 60 megasamples per second. This is not audio. This might be more conducive to a discussion for radars or something like that, or communication systems. But I had the example. I didn't change anything. You can change it to kilosamples per second if you wish. So we know that pi maps to fs over 2, so that maps to 30 megasamples per second, and this point is going to correspond to a third of that. So we see that this spectrum lies between -10 and +10, which is where the original continuous time signal spectrum would lie. Well, okay, now let's look at the other side. So remember, this got stretched out to fill the -pi to pi. I'm not showing any of the replicas here. We established that there's no aliasing in this case. Well, this pi maps to what? This fs over 2. Well, fs over 2 in this case now becomes 20 over 2, or 10. So this triangle lies between -10 to 10, same as this triangle lies between -10 to 10. So it's the same signal, just represented two different ways, two different sampling rates. So this is exactly what we would get if we just took that original continuous time signal and sampled it at its Nyquist rate. Okay, great. Now, I'm not going to show a similar thing when we get to expansion, but the same idea holds. When you're changing sampling rates, you're not really changing any physical frequencies that they represent. Okay, so we did frequency domain for decimation. Now let's do L-fold expansion and look in the frequency domain. So again, we're asking, what is the Z transform of the expanded signal in terms of the original signal's Z transform? And again, we ask the question, what do we expect? Well, we do not expect what a truly upsampled version of the signal, because we're not really, not yet anyway, sampling at a higher rate. We're just inserting zeros to effectively create the impression of a higher rate, but it's got the wrong values there. It's got zeros instead of the values that are supposed to be there. How do we figure out what values are supposed to be there? Well, that's why we're doing this analysis. This analysis will tell us. So let's answer this. Let's do the Z transform of this. So I just purely notationally plug in the expanded signal there into the Z transform expression. But again, like I said, let's think about what that's giving us. Remember, there's L-1 zeros following each non-zero one. So when n is equal to 0, I get x of 0 and z to the 0. And then when n goes to 1, I get a 0, because that's the first 0 stuffed in. And there's another 0. And I get L-1 zeros. And then finally, when I get to n equal to L, well, that maps me back to the original x of 1, but this becomes z to the minus L. And then a bunch of zeros, and then x of 2 with z to the minus 2L, and so on and so on. And so I can just write that out this way. Right? Just think about it. That's exactly what's happening here. As n goes through 0, 1, 2, right? 0, 1, 2, what's happening to the exponent of z? 0 minus 1L minus 2L. So that's exactly what's happening there. Now, if there were no L there, this quantity is xz of z. But there is an L there. So that means I have to put a z to the L raised to the minus n. And so that's what I really have there. So the expanded signal Z transform is just the original signal Z transform. Everywhere there's a Z, we replace Z by ZL, Z to the L. Notice no sums, nothing like that. So the decimation has those sums there because we need to create extra aliasing. But upsampling shouldn't create aliasing. But yet it's going to do something. So let's take a look. Let's convert to the DTFT, just like we did for the decimation analysis. We're going to replace Z by e to the j theta. Again, remember, theta is our discrete time frequency. Rather than omega, I'm using theta. And z to the L will be e to the j L theta, just using properties of exponentials. And so now, if you think about it, when I replace z by e to the j theta, I'd get a function of theta. But now when I'm replacing it by e to the j L theta, instead of having a theta there as the argument, I'll have an L theta. So that's what we end up getting. Remember, we saw theta over capital M was a stretch? Well, now when I multiply by an integer L here, excuse me, that's going to scrunch. Sorry for the overly technical term there. We're just going to squish it in or scrunch it in, but no additional terms added. So let's take a look. When we're thinking about expansion, we can start thinking about something critically sampled. We're sampled at the edge of difficulties, at the edge of problems. If we sample any slower, we'll get aliasing. But we're right at that critical point. And that means if we sample higher, we should get this thing squished in, right? We know that from a regular sampling view. If we took this signal and sampled it higher, we'd get something that looked like this if we physically sampled it higher. That's what we're aiming for. Well, that's the scrunching part here, right? That's the scrunching part. So let's take a look at this. All it does is it takes this thing and it scrunches it in. So everything gets squished. This goes to this region, but this part also gets squished in, not just in width, but in location, right? 2 pi goes to 2 pi over 3. So that's where that's located. So the whole thing, the whole damn thing just gets squished in, and that's what we get. Now, that is not what we're expecting. I'm sorry, have a tickle. That's not what we really want for upsampling, right? If it were upsampling, remember, that would not be there. We'd have this part, but that would not be there. We'd have this, but that would not be there. So we've got extra stuff that shouldn't be there. We're going to have to get rid of that. We'll see how to get rid of that in just a little bit. So the terminology for what's happening here is we say that this expansion, remember, expansion means stuffing in the zeros. We're not yet at a really upsampled signal yet. So the stuffing of those zeros creates these images. And we really can still just look minus pi to pi to see what's going on. And then remember that outside of that, everything is 2 pi periodic. So we get, in this case, for L equal to 3, we get our original spectrum plus 2 images, spectral images. Okay. That's what we'd really like to have if we really sampled 3 times as fast. We'd like these images to be gone. And again, this is ... So we're going to see how to fix that. Now, we're going to take a little interlude here first and talk about the filtering needed for decimation. It turns out that filtering is useful in both of these. We're going to see, let me go back one slide. We're going to see, I'll just give the punchline away. We're going to see that the way we get rid of those images is to apply a filter. So if we put a filter, a nice low pass filter here, we'll get rid of those. And anything that happens in the minus pi to pi is also going to happen outside. That's just how it works. And that would give us this. So expansion followed by filtering, we'll see this in just a bit, works and gives us what we want. But decimation can also benefit from filtering. So let's take a look at that. If the M-fold decimation results in has no aliasing, if the original signal is an nth band signal, we saw that already. But what if we don't have an nth band signal? Then we can't decimate. So here's the idea. We need to ensure that our decimation is not going to create some additional aliasing that we don't want. So we can use filtering to do this. So this is kind of like a discrete time anti-aliasing filter that we're talking about here. So we're going to pre-filter with an M-band discrete time low-pass filter, then do the M-fold decimation. So here's a picture. We start with a signal. Here's its spectrum. It is not an nth band signal. It has some additional stuff out here. And then we're going to run it through this discrete time anti-aliasing filter to create an M-band filter, or signal rather, and then that's the thing we're going to decimate. Now, I know what you're thinking. This spectrum is not this, so I've lost information. Yes, I have. And we can only do this when we don't care about the stuff that's up there. Maybe we're going to handle that separately, or maybe it's a part of the signal that doesn't really matter to us. Or maybe we're just going to live with the loss of that fidelity, right? So those are some higher frequency components in our audio signal, and maybe we're going to filter down to a lower frequency and sample that and live with that. So that's it. That's how we're going to do that. But we'll see that in practical scenarios, we can control all of this. So filter first and then decimate. Now, I don't go into the details of this in this course, but if you were studying a full-blown multi-rate signal processing section of a DSP course, or even better, a whole course on multi-rate signal processing, you'd learn that there is an efficient way to do this filtering and decimate, and that's called polyphase filters. Sounds fancy, sounds like some sort of special filter, but it's not. It's just an efficient way to do this operation. So if you run into these polyphase filters, don't let anybody convince you that they've done some special design to make some sort of special polyphase filter. It's really just a polyphase implementation of this idea. Okay, so that's the need for filtering with decimation. I've already given away the idea of needing filtering for expansion. We had those images. We got those high frequency image spectra that are in there, and we need to get rid of them. And so I alluded to the fact of using a low pass filter to get rid of them. So that's what we can do. We expand. Remember, that's stuffing in zeros. So at this point, we don't really have a truly upsampled signal. We've got all the original samples with some zeros stuffed in between. That creates, at this point, the images, and then the true thing that we want lies in that range, so we filter it out. So here's an example. I'm only showing minus pi to pi, and here is in the time domain the samples of that. And then I upsample, or I expand, and I've stuffed in this case, L equal to 3, 2 zeros after each of my original samples. And what does that do in the frequency domain? The whole point of doing that analysis was to say, this thing ends up here in the right place, but we get the two image spectra that we need to get rid of. But now the filter gets rid of those because it's zero out in those regions. And so now we have this is zero here, this is zero here, and now it repeats 2 pi periodic to show the correct spectral replicas with no images. And what that does is it converts these zeros into the correct values, and it converts these 2 zeros into the correct values, and these 2 zeros, well, I didn't show those over here, and it leaves the original samples right where they should be. Now, at this point, you may be saying, wait a minute, how can this be? How can some filter just convert zeros into exactly the right values? Well, you didn't seem to have any problem with this signal being able to go through a DAC and perfectly create the entire red continuous time signal. So if I can create the entire red continuous time signal, it's actually a little easier to just create a few extra points that lie on that red thing. So that's all I'm really doing. So this is kind of acting like a DAC, a discrete time DAC. It's digital to digital converter. So that doesn't quite have a good ring to it, but that's the idea. And this looks exactly like what we would have. Again, this is all theoretical, assuming we have these nice spectra and we've perfectly band limited ideal filters and so forth. But the reality is, you tell me how close to the ideal you want to get, we can get there. You just might not like the bill. That would include the cost of the processing and the power needed for the processor and all that. But if we can do it perfectly in theory, we can do it arbitrarily closely in practice, however close you want it. And that's the idea. So this is the idea of this post filter. It converts these inserted zeros into interpolated samples. So that's why we often talk about decimation and interpolation rather than decimation and expansion. So interpolation includes expansion, stuffing in the zeros, followed by this post filter that converts the zeros. Here I'm showing the zeros being converted into the values as it runs through that filter. Now for decimation, you don't have to pre-filter, but it usually is a smart thing to do. So expansion and filtering is called interpolation. So here I'm just going to show you, this isn't the full-blown polyphase view, but it's showing you effectively how you could implement this in an efficient way. So here I'm showing explicitly the filter being applied. This is for decimation, filter then decimate. So I apply the filter, I get x hat of n, so there it is. I'm just writing out convolution. So again, if that you look at that and you say, I don't know what that is, you need to go back and study the convolution. I didn't go into a lot of detail in the review, but you can find that in my Signals and Systems course videos that are posted. But what we really are doing is skipping over to every nth output, right? That's this effect. So the decimated signal is the decimation is happening on the filtered signal. There's the hat that it's wearing. And so we jump every m. So let's just take, if I took this n and replaced it by nm, I'm going to take this n and replace it by nm. So what is that doing? Well, remember, our regular convolution is saying lay the signal out, flip the impulse response, and shift it ahead one sample at a time. Each time you shift it ahead, you do the multiplication and the add, and you spit out to get the output. Well, what is this saying? Still flip, that's the minus I, lay the signal out, still flip it, but now you shift ahead by m. So you jump over all the ones that would be really thrown away. So why filter and then throw away some of those that you just worked hard to compute? So this form says just compute the ones you need. No need to throw anything away. And so this is a good thing to remember. Although we don't usually implement it that way, one could. That's where this polyphase filter idea comes into play. So if you want to look in Peratt's book on that or somewhere else. So here we have a staggered output index. This is what controls where we're taking our output from. And that just says what I just said. Let's look at an efficient way to do the expand and filter. So remember, this is stuffing in a bunch of zeros. And then I'm doing a convolution with H. Well, I just immediately wrote that out, right? There's certain values in here that I don't need to multiply by H values. So I would just skip over those H values when I do this sum to compute an output. And so that's what I'm doing here. I'm skipping every elf value of the impulse response shifted to that position. So that is a staggered input index in some sense. And so we don't stuff in zeros before the filtering. Instead, we just take our samples, put them in here, and apply essentially a staggered set of impulse response values. And again, the systematic way to do that is called polyphase filters. So this should give you a brief basic understanding of how we can change the sampling rate. We've only talked about changing it up or down by an integer factor. In the next set of notes, we'll talk about using cascades of these to do any rational sampling rate change. And we'll also talk about some computational aspects of cascading stages. Hope to see you there.